And quantum mechanics is weird. There is no way around it. It's the set of rules that governs the universe at the smallest scales, the world of atoms and photons. And those rules are not like the rules we see in our everyday lives. Things can be in many places at once. They can be both a wave and a particle. An outcome isn't certain until you look at it. It's a strange world down there. The weirdness isn't just some philosophical quirk. It has real, practical consequences. The computer or phone you're using right now works because we understand and exploit these quantum rules. But understanding how to use the rules is different from understanding what they mean. And that's the real problem. For about a century, physicists and philosophers have been arguing about what quantum mechanics is actually telling us about reality. At the heart of the argument is something called the measurement problem. It's a deep contradiction in the theory. On one hand, you have the Schrödinger equation. It's the master equation of quantum mechanics. It describes how a quantum system, like an electron, evolves over time. And it's beautiful. It's smooth, continuous, and perfectly deterministic. If you know the state of an electron now, the equation can tell you its exact state at any point in the future. According to this equation, the electron can be in a superposition, a weird mix of states. It can be spinning both up and down at the same time, for instance. The equation is perfectly happy with this blended reality. But then, we have the other hand. This is what happens when we try to measure the electron. When we look to see if its spin is up or down, we never see a blurry mix. We always get a definite answer. It's either up or it's down. The moment we measure it, the smooth, deterministic evolution of the Schrödinger equation seems to break. The superposition collapses into one single random outcome. This process is sudden, unpredictable, and completely different from the behavior described by the Schrödinger equation. So we have two sets of rules. Rule A, the Schrödinger equation, says things evolve smoothly and deterministically into a superposition of possibilities. Rule B, the measurement rule, says that when you look, everything snaps into one single, random reality. This is the measurement problem. Why are there two rules? What counts as a measurement? Does it have to be a conscious human? A scientist in a lab coat? Does a Geiger counter count? What about a dust particle bumping into the electron? Where is the line between the quantum world of smooth superpositions and the classical world of definite outcomes? This isn't just a small detail, it's a crack in the foundation of our most successful physical theory. For a long time, the standard answer was something called the Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg, the pioneers of the field. Their answer, put simply, was to not worry about it too much. They said that the quantum world isn't something we can visualize or have intuition about. The math, the wavefunction, isn't a picture of reality itself. It's just a tool. It's a mathematical device that lets us calculate the probabilities of getting certain outcomes when we perform a measurement. According to Copenhagen, the act of measurement is special. It's the moment where the fuzzy quantum world is forced to connect with our concrete classical world of lab equipment and eyeballs. In that interaction, the superposition collapses. Why? It just does. Don't ask what reality was like before the measurement. That question, they argued, is meaningless. The only reality that matters is the reality we can measure. This approach became famous for its shut up and calculate attitude, and it works. It allows physicists to make incredibly accurate predictions and build amazing technology. But for many, it felt deeply unsatisfying. It felt like giving up. It introduces a strange and arbitrary split in the world. There's the quantum realm, governed by Rule A, and the classical realm, where Rule B takes over. But the world isn't split. Our lab equipment is made of atoms. We are made of atoms. We are all quantum systems. So why should we follow a different set of rules? Why does the universe care if a collection of atoms is arranged in the shape of a physicist or a rock? The Copenhagen interpretation doesn't have a good answer. It just draws a line in the sand and tells us not to cross it. In the 1950s, a brilliant and unconventional graduate student at Princeton named Hugh Everett III thought this was unacceptable. He looked at the measurement problem and saw a much simpler, more radical solution. He asked a simple question: what if Rule B, the collapse of the wave function, is just wrong? What if it never happens? What if the only rule is the Schrödinger equation? What if that smooth, deterministic evolution is all there is? This seems to fly in the face of what we see. We do see definite outcomes. When we measure an electron spin, we get up or we get down. We don't experience a blur. Everett's genius was in realizing how the Schrödinger equation alone could account for this experience. Here's his idea. Let's say you have an electron in a superposition of spin up and spin down. According to Everett, it really is in both states at once. Now, you, the physicist, decide to measure it. You are also a quantum system, a giant collection of atoms governed by the same Schrödinger equation. When you interact with the electron, you don't magically force it to choose a state. Instead, you become part of the system. You become entangled with it. The Schrödinger equation, when applied to the whole system of U plus electron, says that the system evolves into a new, larger superposition. In this new state, there is a version of U that has measured spin-up connected to an electron that is now spin-up. And at the same time, there is another version of U that has measured spin-down connected to an electron that is now spin-down. Both of these outcomes happen. Both are equally real. They just exist in separate branches of reality. The universe, in a sense, splits. The single reality that existed before the measurement has now become two. One where you saw up and one where you saw down. And the story doesn't stop there. Each of these branches can split again and again with every quantum interaction. This is the many worlds interpretation. It's not that the world might split, it's that, according to the fundamental math of quantum mechanics, it must split. The collapse of the wave function was just an illusion. It was a failure to see the bigger picture. From the perspective of a person inside one of the branches, it looks like a random collapse. You find yourself in the up world and you wonder why you didn't end up in the down world. You can't see or interact with that other version of yourself. The different branches, once they split, go their separate ways. To you, it seems that only one outcome occurred. But in reality, all possible outcomes of every quantum event occurred, each in its own separate world. So, does this idea make sense? It certainly solves some big problems. First and foremost, it solves the measurement problem. There is no more contradiction, there's only one rule, the Schrödinger equation, for everything. Small things, big things, cats, and physicists all follow the same universal law. There's no arbitrary line between the quantum and classical worlds. It's a much more elegant and mathematically clean picture. It also removes the strange, almost mystical role of the observer. In the Copenhagen interpretation, the observer or the act of measurement does something special to reality. In many worlds, an observer is just another quantum system interacting with another. A Geiger counterclicking is a measurement. A photon hitting a rock is a measurement. Every interaction is a branching event. Consciousness has nothing to do with it. The universe evolves on its own, without needing us to look at it. But in solving one set of problems, many worlds seems to create a whole new set of mind-boggling ones. And this is where the debate really begins. The most common and immediate objection is simple. It's just too crazy. The idea of a constantly branching universe, creating trillions upon trillions of new worlds every microsecond, seems like a violation of common sense. It feels bloated and unscientific. This objection is often framed using a principle called Occam's razor, which says that, all else being equal, the simplest explanation is usually the best one. Surely, a theory with just one universe is simpler than a theory with a near infinite number of them. The proponents of many worlds have a clever response to this. They argue that we need to be careful about what we mean by simple. Or is a theory with simple laws, but a complex reality simpler? Or is a theory with complicated ad hoc laws, but a simple-looking reality simpler? Many worlds has the simplest possible laws. It just takes the Schrödinger equation and applies it universally. No extra rules, no exceptions, no collapse postulates. The Copenhagen interpretation, on the other hand, has simpler seeming consequences one world, but its laws are more complex and clunky two rules, and a vague definition of measurement. So, which is truly simpler? A clean equation that generates a messy infinity of worlds, or a messy set of rules that keeps our world tidy and singular? Many world supporters would argue that the simplicity of the fundamental laws is what matters in science. The universe doesn't care if its consequences seem extravagant to us. The second major problem is about probability. Quantum mechanics is famous for being probabilistic. You can only predict the chance of an electron being spin up or spin down. The Born rule, a key part of the theory, tells you exactly how to calculate these probabilities, and it works perfectly. But in many worlds, if all outcomes happen, what does probability even mean? If you're about to measure an electron that has a 70% chance of being spin up and a 30% chance of being spin down, many worlds says that both a spin up world and a spin down world will be created. So, if both outcomes are guaranteed to happen, why do we feel that one is more likely? Why do the probabilities we calculate with the Born rule work so well? This is a very serious objection. It's not enough to say that more worlds are created for the higher probability outcome. The theory needs to explain why our experience matches the numbers. This has been a major focus for defenders of the interpretation. The most promising approach comes from something called quantum decision theory. The argument is subtle. It asks you to imagine you are a rational agent in a branching universe. You have to place a bet on the outcome of a quantum experiment. Even though you know you will split into multiple versions and each version will see a different outcome, how should you bet? Hence, the argument, in a nutshell, is that the only rational strategy for your pre-measurement self is to bet in accordance with the Born rule probabilities. The version of you in the 70% branch will, in some sense, have more weight, or measure, than the version in the 30% branch. Therefore, you should act as if you are more likely to find yourself in that branch. It's an attempt to derive the feeling of probability from the underlying structure of the theory. Not everyone is convinced by this argument. It's complex, and some critics feel it's circular. But it shows that proponents are taking the probability problem seriously. A third objection is known as the preferred basis problem. If the universe is just one giant superposition, why does it split into the particular branches that it does? Why do we see a cat as either alive or dead, and not as some bizarre superposition of alive and dead? Why does an electron split the world into a spin-up branch and a spin-down branch, and not some other set of states? What prefers these particular outcomes as the basis for the worlds? The answer to this lies in a process called quantum decoherence. This is a crucial piece of the puzzle. No quantum system is ever truly isolated. It's always interacting with its environment. Photons are bouncing off it, air molecules are bumping into it. This constant interaction with the environment essentially leaks the quantum information out. The environment, in effect, continuously measures the system. Decoherence explains how a fragile quantum superposition is very quickly forced into a set of stable, classical-like states. The interactions with the environment effectively select a preferred basis. The different branches of the superposition lose their ability to interfere with each other. For all practical purposes, they become separate, independent worlds. Decoherence is what makes the splits permanent and irreversible. It explains why we experience a classical world of definite properties, even though the underlying reality is a vast quantum superposition. The decoherence is now a well understood and experimentally verified part of quantum physics, and it provides a powerful answer to the preferred basis problem, not just for many worlds, but for other interpretations too. Finally, there's the elephant in the room testability. If we can never ever see or access these other worlds, is this really science? Science is supposed to be about making predictions that we can test with experiments. If many worlds makes the exact same predictions for all experiments within our own world as the Copenhagen interpretation does, then how can we ever prove one is right and the other is wrong? Is it just a matter of taste? A philosophical preference rather than a scientific theory? This is a valid criticism. Many worlds in its standard form doesn't offer a unique, falsifiable prediction that would distinguish it from other interpretations. Its supporters would argue that its value isn't in a new prediction, but in its explanatory power. It provides a more coherent, logical, and complete picture of reality that doesn't suffer from the internal contradictions of the standard view. They see it as a better explanation for the data we already have, rather than a machine for generating new predictions. It's a theory about what reality is based on the equations we already trust. To them, that is a perfectly scientific goal. They would say that demanding to see the other worlds is like an ancient astronomer demanding to visit the stars to prove they are far away. We infer their distance and nature from the light we can see right here. Similarly, we infer the existence of other worlds from the quantum mechanics we can test right here. So, what would it be like to live in this kind of reality? The strange answer is exactly like this. The many worlds interpretation doesn't change our experience of the world one bit. You would still feel like you are a single person, making choices and living a single life. You wouldn't feel the splits. The other versions of you, living in other worlds, would be completely inaccessible to you. They are not ghosts or alternate selves in a sci-fi sense. They are just as real as you, but they are on a different branch of reality. When you make a difficult decision, you might feel like you could have gone another way. According to many worlds, you did. Another version of you on another branch made the other choice and is living with those consequences. Every time a random quantum event happens anywhere in the universe, an atom decaying in a distant star, a cosmic ray striking the atmosphere, the world branches. The universe we see is just one infinitesimally thin slice of a vastly larger, endlessly branching multiverse. It's a staggering, almost terrifying thought, but is it sensible? The answer really depends on what you value in a scientific theory. If you value familiarity and intuitive comfort, then many worlds probably doesn't make sense. The idea of countless copies of yourself being created every moment is profoundly strange and hard to accept. Our minds evolved to navigate a single classical world, and this idea shatters that intuition. If you insist that a theory must be ontologically parsimonious, that it shouldn't posit the existence of more things than are absolutely necessary, then many worlds fail spectacularly. However, if you value mathematical consistency and logical rigor above all else, then many worlds starts to look very sensible indeed. It is the most straightforward, literal interpretation of the mathematics of quantum mechanics. It takes the Schrödinger equation, our most fundamental description of how things change, and it just lets it run. It doesn't add any extra rules, any mysterious collapses, or any special status for observers. It gets rid of the measurement problem completely. It paints a picture of a single unified reality governed by one elegant law. The price for this mathematical purity is a reality that is vastly larger and stranger than we ever imagined. Many physicists who work on the foundations of quantum mechanics are drawn to many worlds precisely for this reason. They see the collapse of the wave function in the Copenhagen interpretation as an ugly, ad hoc patch. It's a piece of mathematical machinery that we have to stick into the theory by hand to make it match our observations, but it doesn't flow naturally from the theory itself. Many worlds, for all its metaphysical baggage, is the interpretation that gets rid of that patch. It trusts the math. So, does it make sense? It's a trade-off. You can have a simple-looking reality with complicated and contradictory laws, Copenhagen. Or you can have simple, unified laws with a mind-bogglingly complex reality, many worlds. There are other interpretations as well, each with its own set of strengths and strange consequences. Some theories add new physics, like hidden variables, to explain away the randomness. Others modify the Schrödinger equation itself to include a natural collapse mechanism. None of them are entirely satisfying. Each one asks you to swallow a different kind of weirdness. The debate is far from over. Today, the many worlds interpretation is no longer a fringe idea. It's a serious contender, and its popularity among physicists has been growing. They see its elegance and its power to resolve the deep paradoxes at the heart of quantum theory. But many others remain deeply skeptical, repelled by its ontological extravagance and the lack of testable predictions. In the end, asking if many worlds makes sense is a bit like asking if the idea of a round Earth makes sense to someone who has only ever known a flat plane. It contradicts every intuition. It seems absurd, and yet it provides a better, more consistent explanation for all the observations. The many worlds interpretation asks us to make a similar leap of imagination. It asks us to accept that our personal, unique experience of the world is just one small part of a much grander, branching reality. It's a reality where every possibility is realized, whether that's a sensible price to pay for a more complete and coherent theory of the universe is one of the biggest open questions in all of science. It makes perfect mathematical sense. Whether it makes human sense is something each of us has to decide.